In an experiment to measure the charge of the electron, a spherical charged oil droplet of unknown mass is observed between two horizontal parallel metal plates, as shown in Figure 1. So we've got Figure 1 there with a positive plate at the top, negative plate at the bottom, and the charged oil droplet in between. The droplet falls vertically at its terminal speed when the potential difference, PD, between the plates is 0. A droplet of radius r falls at its terminal velocity v. Derive an expression for r in terms of v, eta, ρ, and g, where eta is the viscosity of air and ρ is the density of the oil droplets. The first thing to bear in mind is that for this oil droplet, if it's travelling at a terminal velocity, it must be in equilibrium. So the magnitude of the force due to drag has to be equal to the magnitude of the weight of the droplet. Now let's draw a free body force diagram for this. Notice how the arrows are of equal length because the forces have the same magnitude. If we write in the expression for the drag and the expression for the weight, so the magnitude of the drag force is going to be 6 pi times eta times the radius of the droplet times v. And the weight is equal to the mass of the droplet multiplied by the gravitational field strength. So let's equate those in the answer space. Now bear in mind that in the question it's not asking for an expression in terms of m. So we need to make substitutions for m. Now density is equal to mass divided by volume, which means that mass is equal to density multiplied by volume. Now bear in mind that this equation needs to also be in terms of the radius, not the volume. So we need to make another substitution for the volume of a sphere. So by substituting the volume equation into the density equation, and then substituting that entire expression in for mass, we arrive at a new expression for the weight of the droplet. Then we need to make r squared the subject of the equation. If we combine the numbers on the top and the bottom, and then finally square root both sides. Now I've made this to the power of half, which is the same as using a square root. In terms of marks for this 2-mark question, the first one is going to be for correctly equating the two forces and making the correct substitutions, and your second mark is going to be for getting the correct expression at the end. Explain how the mass of the oil droplets can be calculated from its radius and other relevant data. Well, first of all, we need to use the previous equation to find the radius. What we can then do is use the equation for the mass that we looked at earlier by combining the density equation with the volume equation. So what we can say there is that the mass is equal to 4/3 pi r cubed rho. So we first of all find the radius from that first equation and then substitute it into the second equation. And that will give our value of m. Now because this is only a 1-mark question, you really only need that second line. A potential difference, PD, is applied across the plates and is adjusted until the droplet is held stationary. The two horizontal parallel metal plates are 15.0 millimeters apart. The mass of the droplet is 3.4 times 10 to the minus 15 kilograms. The droplet is held stationary when the PD across the plates is 1560 volts. Calculate the charge of the oil droplets. The first thing to say about this is that the electric field strength between the plates is not only equal to the force per unit positive charge, but the potential difference divided by the separation. This must mean that F is equal to QV over D. So the charge on the droplet multiplied by the potential difference and then divided by the separation distance. Now bear in mind that this is also equal to the weight of the droplet, which is equal to the mass times the gravitational field strength. We're interested in the charge on the oil droplet, so we're going to make Q the subject and then make the necessary substitutions. So rearranging this equation, we end up with Q is equal to mgd over V, because the charge is what we're interested in. So let's make the substitutions. And that gives us an answer of 3.207 times 10 to the minus 19 coulombs. Now we're going to round that to 3.2 times 10 to the minus 19 coulombs. because the values in the question are to two significant figures, so we need to keep the answer the same. Now for this 2-mark question, we get 1 mark for correctly equating the force from the electric field to the weight of the droplets, and the 2nd mark is going to be for correctly calculating the charge on the droplets. A student carries out Millikan's oil drop experiment and obtains the following results for the charges on the oil drops that were investigated. We've got minus 9.6 times 10 to the minus 19 coulombs. We've got minus 12.8 times 10 to the minus 19 coulombs. And minus 6.4 times 10 to the minus 19 coulombs. You'll notice that those are all multiples of a particular number. Discuss the extent to which the student's results support Millikan's conclusion and how the student's conclusion should be different. Now, the 1st mark in this question is going to be for stating Millikan's conclusion, and that was the charge on an electron is minus 1.6 times 10 to the minus 19 coulombs. Now, this student's results do support Millikan's conclusion because all of the values that are given here are integer multiples of minus 1.6 times 10 to the minus 19. The first one is 6 times that value. The second one is 8 times that value. And the third one is 4 times that value. So there's your first 2 marks. The problem with the student's results is that all of the values the student has obtained are also integer multiples of minus 3.2 times 10 to the minus 19 coulombs. They're all even number integer multiples of that 1.6 times 10 to the minus 19. So the most that the student can say is that the charge on the electron is going to be minus 3.2 times 10 to the minus 19 coulombs. Now, by the smallest quantum, I mean the smallest indivisible package of charge, and that's going to be our 3rd mark. Without Millikan's conclusion, the student wouldn't know that these values are even number integer multiples of the smallest divisible value. So the most that the student can say is that these are all multiples of 3.2 times 10 to the minus 19 coulombs. Figure 2 shows a narrow beam of electrons produced by attracting the electrons emitted from a filament wire to a positively charged metal plate which has a small hole in it. We've got figure 2 there with our coil of wire and then a beam of electrons which escape through a small gap. Notice the potential difference between the 2 terminals. We've got a potential of 0 at the coil of wire and a positive potential which turns the material with the gap into an anode, which attracts the electrons forward. Explain why an electric current through the filament wire causes the wire to emit electrons. Now, when we pass current through any wire, it will cause that wire to heat up because the wire has some resistance. And that's going to be our 1st mark. The 2nd mark is going to be for explaining what happens to those electrons when that wire does heat up. The hotter the wire gets, the more kinetic energy those electrons have because they vibrate more, and eventually they'll have enough energy to leave the wire entirely. And that's going to be our 2nd mark. Explain why the filament wire and the metal plates must be in an evacuated tube. By an evacuated tube, we mean a vacuum, which doesn't contain any gases that you might find in air. Those gases obviously consist of molecules. If electrons pass through those gases, then they're going to collide with the molecules and lose energy. And we don't want that, which is why we use a vacuum. So all you need to say for this question is that the electrons would collide with the gas molecules. So nice easy mark there. The potential difference between the filament wire and the metal plate is 4,800 volts. Calculate the de Broglie wavelength of the electrons in the beam. Now, as soon as you see that phrase de Broglie wavelength, you should think of the de Broglie wavelength equation, which is lambda equals h divided by mv, where lambda is the de Broglie wavelength, h is Planck's constant, m is the mass of the electron, and v is its speed or its velocity. Now bear in mind here that we're not given a speed of that electron. We know the Planck constant is given to us in the formula book, and we know the mass of the electron, that's also given to us in the formula book. But the speed isn't. and we actually have to calculate the speed using 4,800 volts. Now, the equation linking the energy gained by the electron and its speed is going to use kinetic energy. So this is a conservation of energy equation. It's saying that the electrical energy gained by the electron is equal to its increase in kinetic energy. Now what we need to do is combine those two equations together, but keep the de Broglie wavelength for subject because that's what we're trying to find. So this looks a little bit complex, but all I've done is rearrange the energy equation on the right to make lowercase v the subject, speed, and then I've taken that square roots expression and I've substituted it into the equation for de Broglie wavelength. Now all we need to do is substitute in the correct values, and that will give us an answer right. You'll notice that the only value that we need is that accelerating PD. All of those other values, so H, M, and E, are all from the formula book. So even messier again, but you'll notice that I've used Planck's constant, which is 6.63 times 10 to the minus 34. Units aren't important at the moment. We've got the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. And then we've got the charge on the electron, which is 1.6 times 10 to the minus 19 coulombs. In theory, for this question, you could do it in separate steps, but then you risk truncating your value or rounding it and reducing its accuracy. So it's good practice to do all of this in one big equation, in one big calculation. Now I've ended up with 1.772 times 10 to the minus 11 meters. I'm going to round that to 1.8 because then it will be to two significant figures, which is the same as that 4,800 volts that we've been given in the question. Remember, we have to match the number of significant figures because that's the level of accuracy to which we can know our value based on the information that we're given. So a very small wavelength there. Now in terms of marks awarded, they're awarded slightly differently in the mark scheme because it breaks it into two separate steps where you first find the speed and then substitute that speed into the de Broglie wavelength equation. So the first mark is going to be for correctly using that conservation of energy equation and relating the electrical energy to the kinetic energy of the electron. I've combined two steps into one for the next 2 marks. So the calculation that I've put in the middle actually combines a velocity calculation with a de Broglie wavelength calculation. So there are 2 marks awarded there. And then the last mark is going to be for correctly getting 1.8 times 10 to the minus 11 meters. Just be really, really careful with your calculator with that big calculation. If you miss out a value, for example, and then you won't get that last mark for the correct answer. The beam is directed at a thin metal foil between the metal plate and a fluorescent screen at the end of the tube, as shown in figure 3. The electrons that pass through the metal foil cause a pattern of concentric rings on the screen. We've got figure 3 there. Electron beam comes through the metal foil. We get that diffraction effect, which produces rings on the screen. And it's a side view and a front view. The front view just showing those concentric rings as described at the start of the question. The potential difference between the filament and the metal plate is increased. State and explain the effect this has on the diameter of the rings. Now you can technically answer this question in terms of equations. You could talk about the diffraction grating equation and how that is affected by wavelength. And you can link that wavelength back to the speed of the electrons through the de Broglie wavelength equation. But to complete this question in the quickest way, you just need to describe each thing qualitatively rather than using any numerical values. So the first thing to say is that when you increase the potential difference, you're increasing the speed of the electrons. If you want to, you can say that you're increasing the kinetic energy of the electrons. That works as well. And that's going to be your first mark. Your second mark is going to be for saying that the higher speed of the electrons will mean that they have a lower de Broglie wavelength. Remember, the de Broglie wavelength is inversely proportional to the speed of the electrons. And then your third mark is going to be for saying that if the electrons have a lower de Broglie wavelength, they won't diffract as much. And that will mean that the rings become smaller. Now what I'm going to do here is for each point of these 3 that I've made, I'm going to reference the necessary equation that you can use, just so that you can see where each piece of logic comes from. So for the first point, we're referencing the kinetic energy electrical energy equation. For the second point, we're referencing the de Broglie wavelength equation. Notice how the de Broglie wavelength is inversely proportional to the speed of the electrons. Now this third one is a bit of a push, but it's an equation that links wavelength to diffraction angle, and you'll notice that if we're getting a smaller wavelength on these electrons, then the value of sine theta is going to get smaller because we're keeping n and d the same. So n being a given maximum and d being the spacing between the atoms in the metal foil. What that then means is if the value of sine theta gets smaller, then the value of theta will get smaller as well. So very useful three equations there. Maxwell's theory suggested the existence of electromagnetic waves that travel at a speed of the square root of 1 divided by epsilon 0 mu 0. So what we've got there is epsilon 0 being the permittivity of free space and mu 0 being the permeability of free space. Hertz later discovered radio waves and performed experiments to investigate their properties. Figure 4 shows a radio wave transmitter and a detector. The wave is transmitted by a dipole aerial. The detector consists of a metal loop connected to a meter. Now we've got figure 4 here, signal generator connected to a dipole. We've got waves that are emitted and then picked up by a metal loop at the other end where the detector is, and that's connected to a meter. Explain how the detection of the wave by the loop demonstrates the magnetic nature of the radio waves. So fairly straightforward 2 marks here. If we're going to induce an EMF in the loop at the detector, we need to cause a changing magnetic flux in that loop. Now the only way to get a changing magnetic flux is to have a varying magnetic field, and that varying magnetic field is going to come from the electromagnetic wave. And that's going to be our first mark. Now the second mark is more evidence-based. If the electromagnetic wave is causing a change in magnetic flux, then it must have a magnetic nature. And that's going to be our second mark. Explain how the electric nature of the waves emitted by the dipole could be demonstrated. Now, the best thing to do for this one is to get another dipole, which we can then align with that transmitter to see what we get. The dipole can detect an electric field, and if that electric field changes, then there must be some electric field nature to the waves as well as a magnetic field. So a bit of a long-winded answer there. We've got this idea that a second dipole placed near the transmitter, aligned in the same direction, is going to pick up any changing electric field. If the wave has an electric field, then it's going to be picked up by that second dipole. So just 1 mark there. Hertz used an arrangement like that shown in figure 4 to determine the speed of radio waves. Describe how the speed was determined. Go on to discuss how the experiments of Hertz confirmed Maxwell's prediction and the experimental evidence that suggests light is also an electromagnetic wave. Now, it would be advisable to break this question down into 3 parts. It won't be as simple as 2 marks for each of those 3 parts, but we can break it down all the same. So the first section is going to be on determining the speed. The first thing to include would be a diagram with a transmitter and then some kind of surface to reflect the waves back so that we can set up some stationary waves. So we've got our transmitter with a dipole and a reflecting surface at the other end. We've then got the standing wave in the middle. It would be useful to label this diagram. Now to complete this section, we need to talk about how that apparatus and that setup is going to be used. So if we know the frequency, which we can easily find from the transmitter, we can use the equation V equals F lambda by finding the wavelength of the waves, which we obtain by finding the distance between nodes or antinodes. We can then work out the value for V. So that's going to be our first section. The second section is going to be on supporting Maxwell's prediction. The first point to make is that the result that Maxwell got came from a prediction made around electromagnetic waves. What we can then do is use that equation from the top, or that expression involving the permittivity of free space and the permeability of free space. So we can substitute in values from the data booklet, and from that we obtain a value of 2.99 times 10 to the power of 8. So what we find there is that the speed of the radio waves is the same as the predicted speed from Maxwell's equation. And that completes our second section. The last section is going to be on experimental evidence. So we also have an experiment that's carried out by someone called Fizeau, and we need to briefly outline the experiment that was carried out. So what we have here is a source of light, such as a laser. We have a glass panel. We have a rotating disc that has gaps for the light to pass through. We've got a reflecting surface, and then an eye. Now, without going into too much detail in terms of the equations, the speed of the rotating disc is turned up until the light is no longer seen. At this point, when the light can no longer be seen, the light passes through in one direction through a gap, but then when it comes back, it hits a tooth, which has now taken the place of the gap where it initially passed through. And we can use calculations around this to find the speed of the disc. We don't need to go into too much detail here because the assumption is that this section is approximately 2 marks. Now, to make this section relevant, what we need to say is that the speed calculated in Fizeau's experiment is similar to that predicted by Maxwell, which suggests that light behaves as an electromagnetic wave. And that completes our section 3. Now, the reason I haven't allocated 2 marks to each of these sections is that you get a mark for your quality of written communication. So that leaves us with 5 marks for the rest of the content. So typically with this sort of question, if one of your sections has roughly half of its information missing, you might find that you'll lose a mark. If you only have 2 sections at all, with the third one missing, then you might miss a potential 2 marks. So it's roughly estimated that missing half a section loses a mark. But to obtain 4 marks, you definitely need to provide sufficient detail in all 3 of those sections. One of the 2 postulates of Einstein's theory of special relativity is that the speed of light in free space is invariant. Explain what is meant by this postulate. So by saying that it's invariant, what we mean is that it doesn't matter where you are and how fast you're traveling, the speed of light will always remain the same. So what we need to say here is that the speed of light in free space is independent of the motion of the source and of the motion of the observer. That's just the mark there. States the other postulate. Now the other postulate is that regardless of which inertial frame you're in, the laws of physics will remain the same. And that's just something that you need to know. So another easy mark there. 2 detectors are measured to be 34 meters apart by an observer in a stationary frame of reference. A beam of pi mesons travel in a straight line at a speed of 0.95 c past the 2 detectors, as shown in figure 5. So just as we've described there, we've got figure 5, detector 1 and detector 2, and then the pi mesons pass through the first and then the second, which are 34 meters apart. Calculate the time taken in the frame of reference of the observer for a pi meson to travel between the 2 detectors. Now, this is a nice simple speed, distance, time equation. However, we're interested in the time, so we need to rearrange this equation to make time the subject. Now the distance is obvious, it's just 34 meters. However, the speed, it says at the top there, 0.95 c. That means 0.95 or 95% of the speed of light. And we know the speed of light to be 3 times 10 to the power of 8 meters per second. So putting all of those values together, we end up with 1.193 times 10 to the minus 7 seconds. So a very short period of time there. We're going to round that to 2 significant figures because then it stays consistent with the values given to us in the question. So 1.2 times 10 to the minus 7 seconds. So with this being a 1 mark question, the only mark you're going to get is for correctly getting the time taken. Pi mesons are unstable and decay with a half-life of 18 nanoseconds. It is found in the experiments that approximately 75% of the pi mesons that pass the first detector decay before reaching the second detector. Show how this provides evidence to support the theory of special relativity. In your answer, compare the percentage expected by the laboratory observer with and without application of the theory of special relativity. Now let's just look into this question closely and just see where the key pieces of information are that are going to help us to get those 5 marks. Now, the first thing to say is that there are 75% of pi mesons decaying, which means that that percentage of mesons that are left is going to go down to 25%. Now, what you'll notice there is that for something to go down to 25%, you could say that it's halved twice. It's gone down to 50%, and then it's gone down to 50% of that 50%, which is 25%. So that's going to come in useful later. Now, the other thing to say is that we need to compare the percentage expected by the laboratory observer with and without application of the theory of special relativity. So we want to show that 75% agrees with special relativity occurring and what the percentage would be if special relativity wasn't a thing. So the first thing to write down is that where this is dropping down to 25%, 2 half-lives have passed because the percentage is halved twice. And that's in the observer's frame of reference. So you'd actually get 2 marks for making that point. You might want to just be explicitly clear here and say that by halving twice, it's dropped to 25%. Now you can see here that it says the pi mesons decay with a half-life of 18 nanoseconds. Now that isn't really useful to us on its own because we aren't in the pi mesons frame of reference. We're not in its rest frame. We're the observer, so we want to know what happens when that time is time dilated and how we would experience that time as an observer. So if we use the time dilation formula, now you'll notice that that v squared over c squared is the same as v over c as a fraction all squared, and we know that v over c is going to be 0.95 because it's the speed of the muons as a fraction of the speed of light. So it's going to be 0.95. So we can rewrite this. And when we make that calculation, we end up with approximately 58 nanoseconds, which is the half-life of the pi meson in our own frame of reference. Now, for making that calculation and getting the correct answer, you would get another 2 marks. So that's 4 marks out of the 5. What we now need to look at is what would happen if there was no special relativity. You might want to, before you do that though, just point out that this 58 nanoseconds is approximately half of the amount of time that we calculated in the previous question, which was 120 nanoseconds. Just to be explicitly clear to the examiner. Now, if special relativity wasn't a thing, we would find that many more half-lives would have passed, which is just the number of times that 18 goes into 120. Now, for that 5th mark, it's not enough to say that on its own. We would then need to work out what the percentage of remaining muons would be after this many half-lives have passed. So we're effectively halving it 6.7 times. Now, halving it 6 times would mean that we get a 64th of the original number of muons. So it's going to be smaller than that, but not as small as 1 over 2 to the power of 7. So by doing a half to the power of 6.7, we end up with approximately 10%. So around 10% of the muons should be remaining. So 90% should have decayed. And there's your 5th mark.